So this final video for Lecture 8 looks at analysing wedges and belts. So the applications are kind of displayed on slides 23 and 24 of Lecture 8. So you've got a wedge in slide 23 holding some pipes and preventing them from rolling, and then a belt. I think it's fairly obvious that some of the uses of those, but things like around different parts of machinery, driving shafts and things. So what we're going to do is we're going to analyse some of the forces acting in those two different devices. In terms of analysing wedges, if you look at slide 26, you'll see there's two wedges. See my bad drawing again. It's meant to be wedge shaped, this second piece. Let me try and make it more wedge shaped. That's still not wedge shaped, is it? There we go, that's better. I'm pushing it in. There's going to be friction pushing out on both surfaces, and there's going to be contact between both surfaces, and we need to work out exactly what's happening there. And you're going to treat each block, so A and B if you like, as separate blocks and analyse them separately. And that's pretty much all there is to it. The main difficulty comes in the fact that this wedge obviously has an angle associated with it. But it's not too difficult. We draw free body diagrams and treat them separately. And obviously there will be forces here which link blocks A and B. And again, this will become more obvious when we do an example. The second part, looking at belts just very briefly, because it comes up before the examples. On slide 30 there's a point about belts. If it's sat round some kind of curved surface, a pulley perhaps or something. So you've got your pulley and you've got your belt. The angle of contact, which we're going to call that. We're going to call that beta. And what we're saying is that the tension T2, if I'm pulling T2, T1, T2 has to equal T1 e to the mu beta, where beta is the angle in radians of contact and mu is the coefficient of static friction between the belt and the surface it's lying on. The main thing to remember is to use radians for beta. So if it's just about to slip, then T2 has to be larger than T1. That's really all there is to it. If it's about to slip, if I'm pulling on T2 and it's about to slip, you know it's going to be bigger than T1. But if we look at some examples of using that. So the first example begins on slide 31, and you've got a crate weighing 1500 newtons. Coefficient of static friction is 0.3 between all surfaces, and the wedge has negligible weight. And we want to know the smallest force to pull the wedge out. One thing I didn't talk about is if the wedge is the wrong shape, it won't ever come out, and then it's called self-locking. I think it does mention it briefly in an earlier slide. Yes, on slide 29 it mentions it, but so our wedge is beautifully shaped there, that it's designed to come out. So the question we're looking at is something like that. If I was to be pulling it, and it's on a slope, if I was to be pulling it that way, it's never going to come through the gap. Okay, so if I was pulling my wedge that way, it's never going to come through the back gap. That's self-locking. As it goes, our question much simpler than that, and answerable. So we've got P. First thing we'd do is we'd draw free body diagrams for both pieces, so for the crate and for the wedge. You'll notice the crate is against a wall, just there. So as the wedge comes out, the crate's going to move downwards, which is going to cause friction between the crate and the wall. So as that moves out, that's going to move down, and there's going to be friction in that surface there. So we're going to have friction just there, 0.3 NB, where NB is my contact force to the wall. I'm going to have a weight of my crate, which we know is 1500, but I'm going to put W there just to make it look a little neater. If the wedge is being pulled this way, then the crate is going to want to move the opposite way. So the crate is going to want to move this way, which means the friction on the wedge on the crate is going to act that way, the direction we originally drew. So we're going to have 0.3 NC. Right. And if we have an NC, we're going to need an NC there. And similarly, we're going to need a free body diagram for our wedge. So we've got NC is the contact force. Our friction is going to be going the opposite way for the wedge, because the two surfaces are brushing past each other. We're going to have our pull force, P. We're going to have, this is an angle of 15 degrees. So we're going to have ND is going to be at 15 degrees. And we're going to have the frictional force here is going to be going that way. It's going to be 0.3 ND. And then we can start to apply our equations of equilibrium. It's going to be simpler to start with the crate just because there's fewer unknowns and fewer angles as well. So starting with the crate, sum of the forces in the X is NB minus 0.3 NC. And the sum of the forces in the Y direction is going to be NC minus 1500 plus 0.3 NB. We can then solve those simultaneously, and NB comes out at 413 newtons, and NC comes out at 1376 newtons. Now we've got those, we can transfer some of the figures into our equation for our wedge. So again, applying equations of equilibrium, the sum of the forces in the Y, this time for the wedge, it's going to be ND cos 15 plus 0.3 ND sine 15. So ND cos 15 is your contact force in the Y direction. 0.3 ND sine 15 is your frictional force in the Y direction. Minus 1376, that's NC that we've just carried through from the crate. And from that I can straight away find ND, because I can rearrange ND as the only unknown, and I can get 1319 newtons. Some of the forces in the X we can then do is 0.3 times 1376, which is 0.3 NC, it's the frictional force, minus 1319 sine 15, which is my X component of the frictional force in the X direction. No, it's not, sorry, it's the contact force in the X direction, plus 0.3 times 1319 cos 15. That's the X component of frictional force at surface D in the X direction, minus P, which is my push force, or my pull force, sorry. We can calculate P to equal 453.6 newtons. So that concludes all of the questions, apart from one final group problem solving exercise for lecture 8. If you turn to slide 38, no, not 38, 35, sorry, there is a group problem solving exercise which has 2 blocks, one sliding over the other. Tips that I can give you for this before you start: you've got this sort of scenario. First of all, start focusing on this pull force. This pull force is everything we've just been doing. This bit round the wire with the pulley and the D weight is extra. Okay, so work out your pull force to there first. Secondly, there are 2 scenarios that could take place. One, both blocks B and A, both blocks could slide as one whole unit, so they could all slide like that with one mass and one frictional force at the bottom. The second option is that block B could slide off block A with a frictional force just there. So 2 scenarios to consider. You need to work out which one actually takes place. If you pause the video there, have a go at the question and then come back to the video and I'll show you how to solve it. So you should have had a go at the group problem solving exercise that looks a little bit like the diagram I'm showing on the screen at the moment. If we deal, I talked about there being 2 scenarios. If we deal with the first scenario where the whole unit moves together to start with, and we're just looking for the P force initially, so we don't worry about what the weight of the unit D is. We'll just work out the P force, the pull force on block B. Then we can consider we've got one box with 80 newtons down, 50 and 30 added together. We've got one contact force N. We've got one friction force, which is going to be 0.4 N. And we've got one P force there. And we can say the sum of the forces in the Y direction is going to be N minus 80. So N equals 80 newtons. And the sum of the forces in the X direction is going to be equal to 0.4 lots of 80 minus P. So P is going to equal 32 newtons. So, simplest scenario, the whole thing slides as one unit, then the pull force needed to make that happen is 32 newtons. Now let's consider just block B sliding off the top of block A, so just block B sliding. If we redraw block B on its own, then we're going to have, we're told the angle is 20 degrees. Oops, 20 degrees to there. We're going to have 30 newtons acting downwards. We're going to have a different coefficient of friction, it's 0.6 N. We're going to have N is going to be acting perpendicular to the slope. I'm going to have our P force still. So slightly more complex. We're going to have our forces in the Y direction. It's going to be N cos 20 plus 0.6 N sine 20 minus 30. So N cos 20 is resolving the contact force into the Y direction. 0.6 N sine 20 is resolving the frictional force into the Y direction, and minus 30 is obviously the weight. Similarly, we can so we can then find N, and N will be found to equal 26.2 newtons. We can then go on and find the forces in the X direction to equal minus P plus 0.6 lots of 26.2 cos 20. So that's my friction in the X direction. Minus 26.2 sine 20. So that's my contact force N in the X direction. So my pull force can be calculated at 5.812 newtons. So to get just block B to move on its own, this being block B, to get just block B to move on its own, I pull with 5.812. If If I wanted to move them both together, I'd have to pull with 32 newtons. So clearly block B is going to slide on its own first. So the pull force, the minimum pull force at P, which was the bit I added, to get the system to leave static equilibrium will be 5.812 newtons. So if we then consider finally this bit just on its own, we've got 5.812 newtons. We've got weight D. Our weight of D is going to equal our pull force, E to the mu beta, and our mu was given for the pulley or the peg or whatever it is at 0.5. So our weight of D is going to equal 5.812 e to the 0.5, which was given, to the 0.5 pi, because we've got a contact, although badly drawn here, of 90 degrees. So 90 degrees equals a half pi radians. Okay, don't forget to put it in radians. So that's going to be 12.7 newtons. So a block here weighing 12.7 newtons will cause the system to move out of equilibrium and block B slide off the top of block A. That concludes lecture 8, looking at friction and then looking at belts and wedges. Hopefully there are no questions on that. If there are any questions, feel free to email me. You now have a series of tutorial questions that you can have a go at online.